Today we are going to discuss the cosmic microwave background radiation, CMBR. We have already learned about its discovery in the 1960s. This is a radiation which is nearly isotropic, and it was discovered in the 1960s, and its spectrum was very precisely measured in the 1990s, and the spectrum was found to be very well fitted by a blackbody spectrum of temperature 2.73 Kelvin. This was a satellite experiment. The satellite was called Kobe, and the experiment is called FIRAS on the satellite. Satellite was launched by NASA in the 90s, and this experiment established that this radiation, which we see coming from all directions, is indeed a blackbody spectrum, has a blackbody spectrum with temperature 2.73 Kelvin. This is possibly the best blackbody spectrum that has ever been measured till date anywhere, including experiments on Earth. And the error bars here have been magnified 100 times so that they can be seen. They are 1 sigma errors, which are actually 100 times smaller. So this is a blackbody radiation. The peak is in the millimeter, and the bulk of the radiation is in the millimeter and centimeter range of the spectrum, and it is quite isotropic, absolutely isotropic. Okay. Now if you take a closer look, so if you remove an isotropic component, so if you remove a component of blackbody spectrum, so if you remove the radiation corresponding to a blackbody spectrum at 2.73 Kelvin and from all directions, what you have left looks like this. So there is the next thing that you see once you remove this monopole component, so the isotropic component, is a dipole, which is quite visible over here. You see this part is much fainter and this part is much darker. Okay, so this is a dipole pattern. The thing that you see in the center, passing through the center, is the image, is the imprint of our own galaxy. After all, we are seeing the cosmic microwave background radiation through our own galaxy, which leaves an imprint. This can also be removed by doing observation that over a large number of frequencies. Anyway, the main point here is that after you remove the isotropic component, the next thing that you see is a dipole, and the temperature variation of this dipole is 0.0035 Kelvin, 335 Kelvin. So it is around 1% fluctuation. It is a 1% fluctuation. So it is, I said 0.1%, not even 1%. Sorry, this is a 0.1% fluctuation in the temperature. And there is a one direction in which, on the sky, in which the temperature is this much hotter, and another direction in the sky where the temperature is this much colder. Okay, and this dipole pattern in the cosmic microwave background radiation is interpreted in terms of our motion of our solar system. So if the solar system is moving in, this is the solar system, let us say, and if the solar system is moving in some direction, then the photons from this direction with reference, so we are assuming that there is a frame of reference in which the CMBR is isotropic, and if the solar system is moving with respect to that, then the photons from this direction will be blue shifted, and the photons from this direction will be red shifted due to the Doppler shift, and the shift is V by C, which is also proportional to equal. Okay, so the fractional variation in the temperature of the CMBR is directly proportional to V by C. So this is of the order of 0.1%, which straight away tells us that V is of the order of 0.001 into C, which is, and so this dipole can be interpreted in terms of our motion with reference to a cosmological frame of reference where the microwave background radiation will appear isotropic. Okay. Now, if you look at, if you remove the dipole component also, so if you transform everything to a frame of reference where the CMBR, the dipole is not there, the CMBR still has some small anisotropy left. So this is a picture of the fluctuations in the cosmic microwave background radiation after you have removed the main dominant isotropic part and the dipole as well as the contribution due to our galaxy. Okay. So this is a picture of the sky, of the CMBR anisotropies in the cosmic microwave background radiation on the sky after all those things have been removed. The dominant component and the dipole both have been removed. So the fluctuations that remain, you see, are even smaller. They are of the order of 2 into 10 to the power minus 4 Kelvin. And this is an image made by a NASA satellite again called WMAP, Wilkinson Microwave Anisotropy Probe, and the satellite is still carrying out observations. This image shows you the result of 7 years of their observation. Okay, and in this image the redder parts are hotter and the bluer parts are cooler. Okay, so there are so it is, the cosmic microwave background radiation is isotropic to a very large degree. Okay, it's isotropic to a very large degree, but there are minute fluctuations in this radiation, and these minute fluctuations are very important for our understanding of the universe. Let me explain this to you without going into detail. So if you look at the distribution of galaxies in our universe, for example, I have told you that we expect the universe to be homogeneous and isotropic, at least on large scales. Now this image shows you the distribution of galaxies in a part of the universe. Each point here is a galaxy. Okay, the distance was measured using redshifts, and the redshifts are plotted along this axis. So the largest redshift that you have here is around 0.1. Okay. So it is roughly 10% of the horizon size. Okay, 10% of the horizon size, few hundred megaparsecs. Horizon is few thousand megaparsecs. And the other direction is the angle on the sky. So you have the distance from redshift and you have the angle on the sky. So what you see is that it really doesn't look homogeneous and isotropic, homogeneous at least, right? So the point is that there are large scale structures in the galaxy distribution in our universe. Okay, they are not perfectly, so there is a length scale. The length scale is somewhere around 100 megaparsecs, of the order of 100 MPC, maybe somewhat less, maybe somewhat more, beyond which the universe is homogeneous. Okay, but on smaller scales there are considerable amounts of structure, and the study of these structures is a very interesting topic itself, which we shall not go into in this course. These are referred to as large scale structures, and this is showing you the data from the Sloan Digital Sky Survey, SDSS. Okay, so the question is, how do these things arise in a universe which is largely homogeneous and isotropic? So the current belief is, the belief which is also quite well established and well accepted, is that there were initially in the universe some small fluctuations in the density. It was not perfectly homogeneous and isotropic. There were small fluctuations in the density, and these small fluctuations in the density grow by the process of gravitational instability. So what is the process of gravitational instability? In this process, the regions where the matter density is slightly more than average attract the matter from other places, and the region where it is slightly below average, the matter goes out from there. And in this process, and these fluctuations grow as a consequence of that. It's an instability. And as a consequence of this process, you form galaxies. The universe in the past did not have galaxies, nothing. Okay, matter was very close to homogeneous and isotropic. But you had these small fluctuations, and the cosmic microwave background radiation is probing these small fluctuations at a redshift of around 1000. That is the basic interpretation. Okay, so the anisotropies in the cosmic microwave background radiation are probing these small fluctuations at a redshift of around 1000. And these fluctuations grow by the process of gravitational instability to form galaxies and to form this clustering pattern that you see in the galaxy distribution. This again is another redshift survey. Here again the distance is from redshift, and this is the angle in the sky. This is another redshift survey called the 2DF redshift survey, 2 degree field redshift survey. Okay, so the anisotropies in the cosmic microwave background radiation are a very important probe of how these structures formed in our universe, because they allow you to probe these same fluctuations that grow to give you this at a much earlier redshift. And the theory should be able to explain that you arrive from here to here, which it does. Okay. Another point which I should make is that the entire dynamics of this process is dominated by dark matter. So it is the dark matter which, so of the matter in the universe, the baryon, the electrons, protons, the protons and the neutrons make a very small contribution. It is mainly dark matter. So the fluctuations in the dark matter essentially which dominate the dynamics. The dark energy, it is believed, well, dark energy has negative pressure, and it is believed that the dark energy is not affected or does not participate in this process of structure formation except for driving the expansion of the universe. That too beyond a certain, only at low redshifts, not in the at high redshifts. Okay, so this is a brief overview of the cosmic microwave background radiation, particularly what are the crucial points in the what are its crucial properties. So it is largely isotropic. There is a dipole component which we interpret in terms of our motion, and there are other anisotropies once you remove the dipole, and these anisotropies allow us to probe the large scale structure formation in the universe. Okay, now the cosmic microwave background radiation was discovered in the 1960s, and its discovery completely revolutionized our understanding of cosmology. Okay, so let me explain this to you. Okay, so we are, just imagine an observer sitting over here, and we are receiving this radiation which is in which is a black body spectrum. Now if a radiation has a black body spectrum, we know that it originates when a black body spectrum comes about when radiation is in thermal equilibrium with matter at some temperature T. Right, so this is something that we know. So the Planckian spectrum corresponds to radiation in thermal equilibrium with matter. That is the picture that we have. So we imagine a cavity at a temperature T, and if the radiation inside comes to equilibrium with the walls of the with the material inside the cavity, then the radiation has a third Planck spectrum or a black body spectrum. Okay. Now this is the observer, we are sitting here, and we can see inside. So if you look in the millimeter or centimeter parts of the wavelength, or even meter for that matter, parts of the wavelength of the spectrum, we can see objects all the way out to a redshift of order unity and even larger. such objects are visible. So we can identify objects, the universe, till a redshift of order unity, which essentially tells us that the universe is transparent, optical depth to nearly the Hubble to the horizon c by h naught. Right, you are at length scales of the order of c by h naught when you reach a redshift of 1. So the universe, the optical depth all the way to a redshift of order of length scale of order c by h naught is less than 1, because we can see objects over here. If the optical depth was more than 1, the light from those objects would be obscured. So we can see astronomical objects all the way out here, which tells us that the universe is transparent all the way to this distance. So the CMBR photons that we are receiving did not, the fact that the optical depth is 1 tells us that the CMBR photons that we are receiving did not interact with matter within a length scale of the order of c by h naught. There was no interaction. If there was no interaction, how did it come to equilibrium? Right. So this basically tells us that the CMBR that we are seeing did not originate in the nearby universe. The photons, so the CMBR photons that we are seeing because these photons have been propagating freely for nearly the horizon, nearly, not exactly, but length scales comparable to the horizon, all the way out to redshift of order unity and larger, okay, 3, 4, 5, 6, till where you can see discrete objects. Okay. So where did the CMBR photons originate? Where were these photons in thermal equilibrium with matter? So the picture is that if you go back to high redshifts, so if you go to z much greater than 1 or a much scale factor much less than 1, we have seen that the density of matter at those redshifts will be equal to the rho matter naught into a to the power minus 3, because rho into a cube is a constant for matter. Okay. So the matter density in the high redshift universe was much larger. The radiation density, okay, or the temperature of the radiation, we have briefly discussed this, we shall discuss it again, also scales as the present temperature by A. So in the high redshift universe, the density of material was much larger. The temperature of the CMBR, if you just take this, temperature is proportional to temperature into scale factor is a constant, which we have seen by looking at the energy density. We know that the energy density scales as rho r naught a minus 4. This we have worked out, and we also know that this is equal to AB t to the power 4. Right. So from these arguments you can, it is quite clear that the temperature will into the scale factor is a constant. So in the early universe, in these parts in the early universe, the temperature of the CMBR was much hotter and the density was much larger. So sufficiently back in the past, the CMBR, the universe was hot and dense, and the CMBR was in thermal equilibrium with the matter at some high redshift. Okay, so this is the basic picture. So the CMBR was in equilibrium with matter at some high redshift, where the density was much more and the temperature was much higher. Further, if you go back sufficiently into the past, the temperature will at some stage be of the order of 1 MeV. We know that, so I have told you that the temperature increases as inverse of the scale factor. So if you go sufficiently back in the past, the temperature will become of the order of 1 MeV. This is adequate, this is comparable to nuclear binding energy. So all the nuclei will get disassociated. Okay, and so essentially you have the nuclear reactions taking place at those high redshifts, and so you can explain the abundances of light elements, light element abundances, assuming that they were formed in this high density and high temperature material that was there in the universe at high redshifts. Okay, so you can also have nucleosynthesis of light elements. Okay, the heavier elements were made in stars, we have already learned about that. And the nucleosynthesis, the abundance of light elements are found to be more or less the same all through the universe. So this is a natural explanation for that. Now what is the significance? Why is the CMBR so important? Now that we have this basic picture, let us go back to our discussion of the CMBR. So I have told you that the CMBR was discovered in 1960s, and at that time there were two models which were competing in cosmology. One was the evolving universe, which is the model that we have been discussing. So in this model things change with the scale factor. So for example, the matter density is equal to the present matter density a to the power minus 3, etc. Everything evolves with the expansion of the universe. Okay, there was another model at that time which was also competing with this model, which is the steady state model. In the steady state model, there is no singularity in the past. The density of the universe remains a constant. So the universe expands in this model also, that is an observed fact. Both of these models have an expanding universe. But in the steady state model you have to have matter being created so that the density remains constant. Okay, so nothing evolves in this model. On the average, the universe always looks the same as it does now, and the scale factor has an exponential, will have an exponential expansion. There is no singularity. If you have an exponential expansion, the Hubble parameter also remains constant. Here the Hubble parameter is a function of time. It was larger in the past. Okay, in the steady state model you have an exponential expansion where nothing, it's like our cosmological constant dominated model where you have an exponential expansion, the Hubble parameter remains fixed. The universe looks the same all the time. Now you see, if the universe looks the same all the time, it is transparent. We know it is transparent around us, so it will be transparent throughout. It is not possible to, if this was before the CMBR was discovered. Now if you have the universe we know is transparent, we are observer here, we see that the universe around us is transparent. So in the steady state model the universe will be transparent throughout, and the density will not be higher in the past nor will it increase in the future. So in such a model it is very difficult, if not nearly impossible, to produce the cosmic microwave background radiation in a very natural way. Okay, there were methods which were tried out, like the scattering of re-emission of starlight, but these methods did not work. So this model was more or less given up after the discovery of the cosmic microwave background radiation. Okay, because the universe remains transparent all the time and the matter will never come to equilibrium with radiation. Okay, so let me again remind you of the basic picture that we have. The basic picture that we have is that the universe around us is transparent now. The CMBR photons have been propagating freely, and more or less till the till a distance of order c by h naught, the photons have been propagating freely. Somewhere over there at much higher redshifts, much higher than 1, the universe is hot, the temperature of the same sphere is adequately hot and the density is adequately high, so that the matter and radiation are in thermal equilibrium. And if you go back further in the past, the temperature is even higher and you have matter being the nuclei getting disassociated, photodisassociated, and there were no nuclei before that. The temperatures are higher than the nuclear binding energies. Okay. Now with this background, let us so first thing that we shall study is how does the CMBR spectrum evolve? How do the CMBR photons evolve in this regime where they are not interacting with matter? How do the CMBR photons evolve? How does the photon distribution evolve? So to understand this, let us consider a region of the universe of length scale L, a box of length L in all sides. I am just drawing 2 of them. Okay, and the length L, we assume, is much larger than the wavelength of the radiation that we are dealing with, but it is small compared to the curvature length scale of the universe. Okay, smaller than the curvature of the universe. So let us now, so this is a box and we will assume periodic boundary conditions. So the electromagnetic waves inside can be broken up into modes. So the electric field and magnetic field inside can be broken up into modes, and these modes have to be periodic. This doesn't look clearly periodic, but so it basically restricts the wave numbers that are allowed k to be 2 pi by L into nx I plus nyj plus nz k, where nx, ny, nz are integers. So basically they can take integer values 0, 1, 2, 3, etc. Right, because any other value of k will not be commensurate with the periodic boundary conditions. The wave has to repeat after this. So there are only a discrete number of modes which are allowed inside for the electromagnetic wave, which are allowed inside, and they can be labeled by wave vector k, which are enumerated by nx, ny, and z, which can be integers. Okay, and the energy for an electromagnetic wave, we know they are massless. So the energy, okay, before that the wavelength is 2 pi by lambda, 2 pi by k, and the energy is h cross omega E for a particular, corresponding to a particular mode, and this is and the dispersion relation we know for massless for electromagnetic waves, since they are massless, the dispersion relation is that omega is equal to ck. So this is the energy is h cross omega h cross c into k. So corresponding to each mode, the so the photons will occur only with certain k vectors, and the one photon of a particular k vector will have an energy ek, which is h cross into ck. Okay, and the k's are labeled by nx, ny, nz, which can only be integers. Right. So now in thermal this is the situation, and we know that in thermal equilibrium, so if the photons inside are at thermal equilibrium at a temperature T, then the photon occupation number, the occupation number of each mode so this tells us how many particles are there in each mode, or how many photons are there in each mode. So for a boson, Bose gas, it is given by 1 by exponential h cross omega, or okay, h cross omega by kBt minus 1. This gives the number of particles in a particular mode. Okay, on the average. So if I this is a statistical thing, so this is the mean number of particles in a particular mode. So the electromagnetic wave inside this, waves inside this cavity can be decomposed into set of discrete modes, and we can ask the question how many particles are there corresponding to each mode, and the mean number of particles corresponding to each mode, we cannot predict exactly how many there will be, because this is a statistical thing, it's in equilibrium with at a temperature T. What we can predict is that the mean number of particles is given by this. Okay, this is for photons, a black body, so photons in thermal equilibrium. In general, let me write down the general expression. In general, the occupation number of any mode is given by exponential 1 by exponential the energy of that mode epsilon minus the chemical, this is the energy of the particular mode, minus the chemical potential which describes the entire system, divided by kBt plus minus 1. Okay, plus is for fermions and minus is for bosons. So fermions are particles that have half integer spin, half for example, and these are particles that have spin 1, 0, etc., 2. Okay, mu is the chemical potential which determines the total number of particles, which is determined by the total number of particles and T is the temperature. So in thermal equilibrium, so if the particles here, I could have bosons or fermions, whatever, in thermal equilibrium the entire distribution is described by two things, the chemical potential and the temperature. Okay, chemical potential and temperature, and the distribution is different if they are fermions and if they are bosons. Okay. Further, if the particles are relativistic, then we have already written down that epsilon k is equal to h cross into k into c omega into h cross omega basically. Whereas if they are non-relativistic, or in general, let me write down in general, so if they are massless particles, that is this, in general the relation is that epsilon k the energy of a particle is m square c4 plus p square c square, and we know that p, the momentum of a particle, is h cross into k, the wave vector, elementary quantum mechanics. Okay, so this is this plus h cross square k square into c square. Okay, or you can write it in terms of p also, whichever is convenient, p square c square. Fine, and if you look at the non-relativistic limit, then this term is much small compared to this. So you can do a Taylor series expansion, and what you have is that the energy is mc square plus p square by 2m, where p has to be calculated this way. Okay. So in thermal equilibrium, the entire thing is described by this, by a distribution function, by the occupation number of each mode, and this is the situation that we are dealing with. Now let us see what happens. So suppose, let us assume that my system, my particles are in thermal equilibrium to start with. Okay, at some time they are in thermal equilibrium. Okay, so at some epoch, somewhere here, my system, my entire thing, set of particles are in thermal equilibrium at some temperature T, after which they just evolve freely. So what happens when they evolve freely? This is in thermal equilibrium. Okay, what happens when the entire thing evolves freely? Let us just ask that. So if the system evolves freely, so we are assuming that the expansion of the universe, the evolution of expansion, is on a time scale which is much larger than the inverse of the frequency of the radiation, of the wave. Okay, so we can assume that the expansion, all that the expansion does is that it does not, so this box that we are dealing with will basically expand due to the expansion of the universe, and we are assuming that the expansion is adequately slow, and the oscillations that take place in the electric field and whatever in the wave are much faster. Under this assumption, you can assume that all that happens is that the wavelength will get stretched proportional to A of t. This we have seen. The wavelength of each mode gets stretched proportional to A of t. The number, occupation number, so the number of particles in each mode, in a particular mode, does not change. So all that happens due to the expansion of the universe is that the value of k corresponding to a mode will get different, but the number of particles will not change. Okay, so there is a particular mode we are looking at. The k value corresponding to that mode will change because of the expansion of the universe. The wavelength will change, so the value of k will change, but the number of particles occupying that mode, the occupation number, that value will not change. Okay, so given this, let us see what happens to the distribution function or occupation number as the universe expands. So this is, let us say, the starting occupation number, and let us assume that it is relativistic. So for a relativistic distribution, okay, before we start that, so the basic assumption is as follows, that the occupation number at some mode k initially, this is initial, will be equal to, or let me put it other way around, the final occupation number of a mode k, if I want to calculate this in terms of the occupation number at some, so this is the value of the scale factor here is AF. I want to calculate the occupation number of a mode at this epoch. I have told you that the value of the number of particles in this mode will not change. All that will happen is that I have to now, the value of k will change. So this will be equal to the occupation number of a different mode, and the mode that I have to look at, so the wavelength scales proportional to A, so the value of k will scale inversely, right. So I have to look at if I go into the past, I have to look at a value of k which has a higher k value, because this k value, this mode would have had a higher wave number in the past. So I have to look at a mode which is AF, k into AF by AI at the initial. So the final distribution function will be the initial function, distribution function, evaluated at a different mode k value. Then the different k value is the k value I am interested here, scaled appropriately like this. Okay, so let us assume that we have a distribution function like this to start with for a relativistic particle, and we know, let us assume that we know that the distribution function is initially has a temperature Ti and a chemical potential mu I. So we want to calculate the final distribution function. Okay, so the initial distribution function is for relativistic particles. It has an initial chemical potential mu I, initial temperature Ti. Okay, so what we would like to do is that we would like to calculate final, this will be equal to, so I should calculate the initial distribution function. This is equal to the initial distribution function, which is given by 1 by exponential, this will be E is, we know, h nu minus the mu, but the nu that you have to calculate here is not corresponding to this mode k, but it is corresponding to this mode k scaled with AF divided by AI. So I have to put a factor of, let us call this factor x, so I have to put a factor x over here, where x is equal to AF by AI. Okay, so I have to evaluate this not at the same frequency corresponding to this wave vector, but at a different frequency which is x times this value. Nu is proportional to k, so nu also will get scaled with x, minus the initial chemical potential divided by the initial temperature plus minus 1. This is for relativistic particles. Okay, so this is the final distribution function. So you can see that we can write the final distribution function as 1 by exponential h nu minus mu f by Tf minus plus minus 1. So I am redefining this as h nu minus mu f by kb, so there should be a kb here, kb Tf plus minus 1. So how should you define mu f in terms of mu I? So mu f should be equal to x into mu I, and Tf should be x into, rather Ti should be x, right, Ti should be x into. So if you can identify, if you identify Ti to be x into Tf and mu I to be x into mu f. So with this identification, the x will cancel out throughout and you will be led to this. Okay, so what we see is that the final temperature Tf is equal to So for relativistic particles, what we saw is that if the particles evolve freely without interacting with anything, then due to the expansion of the universe, all that happens is that the wavelength corresponding to these particles scales proportional to a, or the momentum scales as 1 by a, because the momentum is inversely proportional to wavelength. Okay, due to the expansion of the universe, momentum scales as 1 by a, and if I start off with a thermal distribution function, at some epoch, then it remains a thermal distribution function, only the temperature and chemical potential get scaled like this due to the expansion of the universe. That is the crux of this whole thing. So they will scale proportional to a. Okay, inversely proportional. So Tf into Af remains a constant. So if the universe expands, the temperature of the black body radiation, for example, they are relativistic particles, will fall as inversely with the scale factor. Okay, so in the epoch when the radiation does not interact with matter, you only have the expansion of the universe. In this epoch, the temperature, the entire spectrum of the black body radiation, it remains a black body spectrum. All that happens is that the temperature scales as inverse of the scale factor, and if there is a chemical potential for black body radiation, it is 0, but if it is some other kind of particle, fermions, etc., the chemical potential also will scale same as the temperature. Okay, now we can repeat the same exercise for non-relativistic particles. So we have to do the same thing again. So we want to calculate the occupation number the final occupation number for non-relativistic particles. We know that the initial occupation numbers are described like this. Okay, so let me write down the initial occupation number first. So the initial occupation number, let me write it here. Now for non-relativistic particles, we have seen that the energy is p square by 2m plus mc square. This mc square term can be absorbed inside the chemical potential here to redefine the chemical potential. Okay, so what we have here then is minus p square by 2m plus mu tilde by kb t plus minus 1. where the mc square term I have put inside mu tilde. Okay. Now, so this is the initial distribution function, and we have seen that due to the expansion of the universe, what will happen is that this will be equal to the initial distribution function scaled by AF by AI. Okay, so P and K are proportional. So what you see is that now this will be equal to, again calling this factor x, this will be equal to 1 by exponential minus p square x square by 2m minus mu tilde by kbt initial mu initial plus minus 1. So if you define Tf is equal to x square, here you have to define Tf to be x square into t initial, so Ti, sorry, so Tf into x square should be t initial mu f into x square should be mu initial. With this you recover the same distribution with new new temperature and new chemical potential. Okay, where the new chemical potential Tf and the new chemical potential are related to the old ones like this. Or what we see is that the temperature now scales as so the scaling is different for non-relativistic particles as from relativistic particles. Okay. Now neutrinos are a very interesting case. So neutrinos, for neutrinos or any such particle, the energy if the temperature is much larger than mc square, then we can treat them as relativistic particles. If temperature is much smaller than mc square, they behave like non-relativistic particles. Okay, so for both these situations the distribution will behave differently with the expansion of the universe. Now if the neutrinos, the other interesting thing is that if the neutrinos go out of thermal equilibrium in a regime where the temperature is much higher than the mass, suppose the neutrinos go out of thermal equilibrium in a regime where the temperature is much higher than the mass. Okay, then the distribution function gets fixed. The occupation number doesn't change again due to the expansion of the universe. All that changes is that the scaling of each mode. Okay, so let me bring today's discussion over here and about how the distribution function changes during the free evolution of the universe, and in the next lecture we shall resume our discussion about the thermal history of the universe based on this. Are there any questions? Would you follow this, or it was okay? So it is, I said 0.1%, not even 1%, sorry, this is a 0.1% fluctuation in the temperature. And there is a hot, one direction in which, on the sky, in which the temperature is this much hotter, and another direction in the sky where the temperature is this much colder. Okay, and this dipole pattern in the cosmic microwave background radiation is interpreted in terms of our motion of our solar system. So if the solar system is moving in, this is the solar system, let us say, and if the solar system is moving in some direction, then the photons from this direction with reference, so we are assuming that there is a frame of reference in which the CMBR is isotropic, and if the solar system is moving with respect to that, then the photons from this direction will be blue shifted, and the photons from this direction will be red shifted due to the Doppler shift, and the shift is V by C, which is also proportional to equal. Okay, so the fractional variation in the temperature of the CMBR is directly proportional to V by C. So this is of the order of 0.1%, which straight away tells us that V is of the order of 0.00. Okay, and in this image the redder parts are hotter and the bluer parts are cooler. Okay, so there are so it is, the cosmic microwave background radiation is isotropic to a very large degree. Okay, it's isotropic to a very large degree, but there are minute fluctuations in this radiation, and these minute fluctuations are very important for our understanding of the universe. Let me explain this to you without going into detail. So if you look at the distribution of galaxies in our universe, for example, I have told you that we expect the universe to be homogeneous and isotropic, at least on large scales. Now this image shows you the distribution of galaxies in a part of the universe. Each point here is a galaxy. Okay, the distance was measured using redshifts, and the redshifts are plotted along this axis. So the largest redshift that you have here is around 0.1. Okay, so it is roughly 10% of the horizon size. Okay, 10% of the horizon size, few hundred megaparsecs. Horizon is few thousand megaparsecs. And the other direction is the angle on the sky. So you have the distance from redshift and you have the angle on the sky. Today we are going to discuss the cosmic microwave background radiation, CMBR. We have already learned about its discovery in the 1960s. This is a radiation which is nearly isotropic, and it was discovered in the 1960s, and its spectrum was very precisely measured in the 1990s, and the spectrum was found to be very well fitted by a black body spectrum of temperature 2.73 Kelvin. This was a satellite experiment. The satellite was called Kobe, and the experiment is called FIRAS on the satellite. Satellite was launched by NASA in the 90s, and this experiment established that this radiation, which we see coming from all directions, is indeed a black body spectrum, has a black body spectrum with temperature 2.73 Kelvin. This is possibly the best black body spectrum that has ever been measured till date anywhere, including experiments on Earth. And the error bars here have been magnified 100 times so that they can be seen. They are 1 sigma errors, which are actually 100 times smaller. So 1 into C, which is, and so this dipole can be interpreted in terms of our motion with reference to a cosmological frame of reference where the microwave background radiation will appear isotropic. Okay. Now, if you if you remove the dipole component also, so if you transform everything to a frame of reference where the CMBR, the dipole is not there, the CMBR still has some small anisotropy left. So this is a picture of the fluctuations in the cosmic microwave background radiation after you have removed the main dominant isotropic part and the dipole, as well as the contribution due to our galaxy. Okay. So this is a picture of the sky, of the CMBR anisotropies in the cosmic microwave background radiation on the sky after all those things have been removed. The dominant component and the dipole both have been removed. So the fluctuations that remain, you see, are even smaller. They are of the order of 2 into 10 to the power minus 4 Kelvin. And this is an image made by a NASA satellite again called WMAP, Wilkinson Microwave Anisotropy Probe, and the satellite is still carrying out observations. This image shows you the result of 7 years of their observation. So this is a black body radiation. The peak is in the millimeter, and the bulk of the radiation is in the millimeter and centimeter range of the spectrum, and it is quite isotropic, absolutely isotropic. Okay. Now, if you take a closer look, so if you remove an isotropic component, so if you remove a component of black body spectrum, so if you remove the radiation corresponding to a black body spectrum at 2.73 Kelvin and from all directions, what you have left looks like this. So there is the next thing that you see once you remove this monopole component, so the isotropic component, is a dipole, which is quite visible over here. You see this part is much fainter and this part is much darker. Okay, so this is a dipole pattern. The thing that you see in the center, passing through the center, is the image, is the imprint of our own galaxy. After all, we are seeing the cosmic microwave background radiation through our own galaxy, which leaves an imprint. This can also be removed by doing observation that over a large number of frequencies. Anyway, the main point here is that after you remove the isotropic component, the next thing that you see is a dipole, and the temperature variation of this dipole is 0.0035 Kelvin, 335 Kelvin. So it is around 1% fluctuation. It is a 1% fluctuation.